Hello and welcome to Open Science. I'm Dr. Marshall Porterfield from NASA headquarters in Washington, D.C. And joining me today is Dr. Mark Weislogel from Portland State University. Mark, you've been a principal investigator for our complex fluids experiments for a number of years, and we've all seen the videos of astronauts playing with spheres of water in space. This is your research area. Can you explain the general phenomena and then talk to us a little bit about what you discovered in your International Space Station research?
People don't understand that a lot of the forces that we see on the ground are the same in space. Those actually don't change. But what does change is the impact of gravity. So with less gravity, then we start seeing small forces that we're not accustomed to dominating the fluid process. So we see giant spheres of liquid, we see giant bubbles, we see liquid going to places where they're not used to seeing. They see this absence of an up or down kind of thing, floating or sinking. Those things all go away, and so that catches us by surprise. And so there's really a lot to learn to make systems work in space.
So how has what you have learned in your research program contributed to the development of a more reliable spacecraft and technologies that are needed to support humans in space?
Okay. It's kind of, another thing is kind of odd, is that almost nothing, no fluid systems that we have on Earth will just work. You just take it to space and it'll work. Most of the systems will be corrupted by large bubbles plugging lines or liquid spilling and going someplace they shouldn't be, that kind of a thing. So as soon as we learn how to position and make fluids do things on their own using surface tension and not, say, gravity, then we learn how to expect where the liquid should be so that we can make refrigeration systems work, make filter systems work, make cooling systems work, make drinking systems actually work, that kind of thing. And so all of our work, even though it tends to be fundamental, has immediate application, we find, to systems that are on spacecraft.
So one of the most popular new things that I've seen that's a result of your work is the development of the coffee cup for the astronauts to use in space. And the shape is very interesting. Can you tell me a little bit about the geometry of the coffee cup and very quickly so that we can understand?
Yeah. Well, the coffee cup actually utilizes all we've learned about capillary stuff in space. And you can learn a lot of that stuff on the ground too, but in space you see it on a big scale. With that, we can make a cup large enough to still exploit capillary forces so that when the astronaut brings it to his face, there's a gradient in the driving force from surface tension to drive that liquid right into the mouth of the astronaut. In a way, we've designed a cup so that the bottom of the cup is actually the lip of the cup. So but when the astronaut makes that connection, that serves as the bottom, and it will drain the cup into his mouth at the rate that he or she takes it in.
Yeah, the video of seeing the astronauts use the coffee cups and the drinking process is very interesting. I'm sure that the audience is really going to enjoy getting a chance to see those videos also. But in addition to the coffee cup, your research has contributed to development or the modification of other hardware systems that are very important on the International Space Station. Can you give us some examples of that?
Right. So in the coffee cup actually has a lot of science in it, and engineering too. So if we can design a system, for instance, for processing urine or processing wastewater other streams or condensing streams of water by just having a simple, maybe it's a complex shape, but a simple non-moving part shape that make all the liquid go to one place, then we can get it out. We can get the bubbles out, we can get the liquid out, we can keep the system operating, and with no moving parts, with no electrical power, just the surface shape, just the shape of the container and the wetting properties and surface tension of the liquid.
So how long have you been involved with this type of research?
Well, when I was a master's student, I saw some images of low-gravity fluid phenomena and got absolutely hooked. That drove me to look for a job at NASA, got one, and for the first decade of my career, I worked at NASA. So this was in my blood. Then when I finally wound up in academia, then I worked like crazy to try and continue that research. It's my favorite thing to do.
So in addition to the work that's being done on the space station and the application to supporting astronauts right now on the space station, how does your research benefit us back on Earth?
We have a unique focus because we see gravity-less processes, things that you don't see on Earth very often because gravity masks everything. But for microscale systems, all this stuff applies. So everything we learned in space is directly applicable to the ground systems, so that when we see all of these biological processes, small flows, wetting and spreading flows, we have almost immediate tools to apply to those systems to make them work better. And so from lab-on-chip technology stuff to medical tubing and things like that, we can have direct impact, and we definitely want to go that direction.
And what about the journey to Mars? Where do you see your research having the most impact in terms of the journey to Mars?
In that one, we think that we can have a very significant impact. Now, our stuff won't displace other methods that are being used, but we might, and we definitely teach how to avoid catastrophe due to capillary failure, like a bubble fouling the system. And we definitely make systems that are more reliable, that free up astronaut time to do other research, not just maintain the systems, that are passive with no power requirements and things like that, or even are redundant, meaning they're silent in the background, continuing to function, even though a primary system may be at work. So it makes systems much more reliable. There's definitely multiple systems, multiple technologies that are making the system function. For life support, that would be a very nice thing to have.
Well, I think another area you need to think about too is the quality of life, because crew performance is tied to quality of life, and just the coffee cup itself, I think, is really a major contribution because that's something that people always do and reminds them of home.
Right. In fact, the coffee cup, their aromatic drinks, would be much more desirable in a cup. Well, the astronauts might have to do the dishes every now and then, but that could be a real advantage too, because hey, there's tons of bags that are being thrown away every time a drink is drank. So that you could actually have a significant savings if you use something like a cup. And this last demonstration is, hey, you can have scalding drinks in open containers safely, just like you do around your coffee with your coffee cup around your laptop in the morning.
That is awesome.
Thank you, Mark. Drinking coffee in a work environment is an important part of life on Earth. And because of your work, now it's possible off the Earth as well. To learn more, go to nasa.gov.